Very much. I first want to thank the organizers. It's a real privilege and a pleasure to be able to give this talk, and always thrilled to be back in Santa Barbara. So I want to talk today about some new insights into particularly the issue of seed formation of the earliest black holes from these high redshift JWST data. And you may notice that I have marked out in orange 3 people, Marta, Rafaela, and Andrea. So 15, 16 years ago, without giving the exact time because it'll date us all, we were the people who were pushing for the idea of a potential new channel other than population 3 to form the first black hole seeds. And even till about 5 years ago, we really had to, at various meetings, defend this idea rather vociferously. And I think all I can say is that the universe has actually been rather kind to us with one very specific object that I'm hoping to show you has provided very compelling evidence for the possible existence of multiple seeding mechanisms. So first of all, I want to clarify that when many of us give talks about massive black hole seeding models, direct collapse channels, and so on, this is not precluding other models. We're just saying that in addition to population 3 remnants that are likely light seeds, that we have other channels. So let me give you a brief outline of the talk. I want to give you what I believe is an ongoing supermassive black hole revolution. We've had insights, as you've seen from many of the wonderful talks that we've seen today. In particular, we saw Dale's talk, we saw Hannah's talk. There's a real sort of bursting of individual sources of individual black holes ranging from redshifts 4 and beyond. And what JWST has really done is open up a unique set of sources at redshifts greater than 10, and that's where I will be focusing later on in the talk, because the closer we get to the seeding epoch, the tighter the constraints we can actually get on seeding itself. And of course, as you all know, nanograph provided the first evidence for the integrated gravitational wave emission from merging supermassive binary black holes, supermassive black holes, and that tells us that there is a growth channel from merging, which was also, remember, all of this was theoretical speculation in terms of the various growth channels, not just the birth channels, but the growth channels. So I think for me, what has been really exciting to watch is how we've moved from finding these individual sources to now starting to really image also the hosts of these quasars at redshift 7, which I think it's just remarkable. And you all saw this very, very exciting data from the pulsar timing arrays, in fact, the entire IPTA arrays from around the world that reported the evidence for the gravitational wave background. And so here, there's a very interesting conundrum, and I point this out because it's relevant to the kinds of number densities, the overabundant black holes. Black holes appear to be littered everywhere in the universe. So one interesting thing is that the inferred amplitude of the strain from this merging population, remember it's the entire population integrated throughout cosmic time, is higher than predicted by the supermassive black hole growth and evolution models that the rest of us have been working with that are in multi-wavelength data ranging from X-rays to UV and so on. So obviously there's something interesting going on with our understanding of how many black holes, the census of black holes. I think there's evidence is kind of incomplete, which I think is an exciting problem. So I will first show you this slide that many of you have probably seen, various versions of this, and that has to do with the various channels for the formation of the early seed black holes. So as you all know, one very natural channel, because stellar evolution has been proved beyond doubt in terms of the larger details, and we know that the IMF is likely top heavy, although we don't know how, it hasn't been accurately quantified because that's done only with simulations at the moment. There are lots of challenges. So you expect remnant seeds that are about 10 to 100 solar masses that are referred to often as the light seeds. Then it has been realized that there ought to be other channels, other ways of making heavier seeds, and that there are incubators. Nuclear star clusters could act as incubators where you could form heavier seeds, and there are multiple channels. So a very nice early paper was by DeVecchi and Voluntari that showed that you could have a star cluster that forms, you could have remnant black holes that merge, and that can give you, over a reasonably quick, cosmically speaking, quick period of time, something that you could end up with 1,000 to 10,000 solar masses. So then there was this sort of channel that several of us realized at roughly the same time. Marta Voluntari and Mitch Begelman and Giuseppe Lodato and myself, we were looking at this idea of trying to see if there was a way in which you could bypass traditional stellar evolution and still make a massive black hole seed. And so we worked on many different settings. And the settings, I'll talk a little bit more about the different settings, and there's been a lot of refinement in our understanding. When we started working on this problem, it was not tractable with simulations, right? Given the resolution and the physical processes that were implicated, we wanted to do this in a cosmological setting, but it was the microphysics of what was happening inside atomic cooling halos that was most relevant, that could not be simultaneously modeled. And there have been major improvements, but I just want to alert you that there is not yet a single simulation that can actually form a black hole, a massive seed black hole, ab initio, if you will. So anyway, these channels can give you seeds that are between 10 to the 4 to 10 to the 6 solar masses from the get-go, right? And they need a set of conditions that need to be satisfied for, and as I said, the various models involve looking at these settings. So what I want to show you is a brief synopsis of the work that's been happening in the field, where people are looking at multiple ways to effect direct collapse black holes. What are the cosmic settings in which you could get direct collapse? And as I want to caution you, not all the final steps are done. They've not been followed in simulations, but we can see. So for example, these are slices from a simulation by Latif and collaborators, where they are looking at turbulent cold flows using the adaptive mesh refinement code ENSO. And they detect onset of direct collapse, and they see very dense, condensed, turbulent cores forming. And these will inevitably, you don't see them, you can't follow them, you don't have the resolution, but they will eventually lead to the formation of black hole seeds. And this is a scenario that could work at redshifts, could commence. We have the conditions in the lambda CDM universe for these conditions to commence at redshifts greater than 20. Right, so there's this kind of scenario where you can form black hole seeds with direct collapse. However, the relationship of these direct collapse black holes to their environments, to their host galaxies, is not predicted yet in this scenario. Okay? So there is another scenario that, again, I want to alert many people in the audience who worked on it. I want to call out Fabio Pacucci, Andrea Ferrara, who've made some really seminal contributions that allowed us to actually play out this full scenario. And so again, this is a scenario that could easily work at redshifts of 15 to 20. So once again, I'm sort of showing you by redshift, you know, these various mechanisms. And so it's a very specific scenario, and we realized that this specific scenario would work because we were looking at a cosmological simulation, the first billion-year simulation box that was done by Sadek Kochvar and his collaborators in Germany. We started looking at the sites and the properties of atomic cooling halos in that simulation, and we realized that there were certain settings that are quite endemic to lambda CDM in the sense of hierarchical structure formation. So you have a parent halo, you'll have a lot of satellite halos, and you see that structure emerging at very, very high redshifts. So in this particular scenario, we noticed that you could have a parent galaxy that has had a first episode of POP3 star formation, so you have star clusters that have formed already, so you have a convenient external radiation field that's coming out of these sources. And then you have a satellite, you typically have satellites around these parents, and you have a pristine atomic cooling halo that is irradiated with Lyman-Werner photons. This is critical because, remember, one of the conditions we wanted for the formation of direct collapse black holes was the suppression of molecular hydrogen cooling. So we want inefficient cooling, fragmentation, star formation. So you want star formation to be suppressed as much as you can to effect direct collapse. And so then the idea is that you would form per lambda CDM a very gassy, massive disk This is pre-galactic, so no stars are formed in this atomic cooling halo, and that gas disk would then go globally unstable, and you could form a direct collapse black hole. However, this being a satellite, it would rapidly merge. This is all again within the context of CDM, right? So it's very much embedding the picture in the CDM story. You would end up with a very peculiar kind of beast where you inherit the stellar component of this galaxy, the parent galaxy, and the direct collapse black hole, and some gas, and so on. So this object, we realized immediately when we did a first set of calculations, would have an overmassive black hole compared to the local relations that we see for black holes, black hole mass versus stellar mass. But this is at extremely high redshifts, right? And so then we also realized, thanks to the 1D hydro code that developed by Fabio during his PhD with Andrea Ferrara, that we could then actually calculate in a simple way the evolution of this object over time, still at very early times. And in post-processing using Cloudy, we could actually calculate the output multi-wavelength spectrum. So that was this scenario, we were able to close the entire loop, connect it to JWST observable. So that was what was unique about this. That's what this scenario presented to us, and we were able to do it. And then we were able to compare and contrast what would happen if you had a light seed. And so we were able to compare, predict spectra, classes of spectra. In fact, we have a library of spectra. As you can imagine, there are lots of parameters here, gas density, the temperature, the density, as well as the spins of these halos. Remember, it's all embedded in CDM. So you have a lot of interesting parameters, and so we have a full parameter library. And then we have assumptions that we can make about the accretion onto the black hole itself, whether it's Eddington limited accretion, so it's a thin disk, radiatively highly efficient, or we can we did a toy model for a radiatively inefficient flow that could give you super Eddington accretion rates. So we had a library of template spectra that we produced. And this we did in 2017 before JWST flew as predictions for this particular scenario. So not only were we able to predict the spectrum, but we were able to develop tracks and color plots. I'll show you some of these. And so these predictions were made for this particular class of direct collapse models where you would have transient overmassive black holes, so before the stellar component speeds up. So here's another direct collapse scenario, which is a bit of a riff on what we came up with, and this is done by Barrow and Wise. And what they argued is that, great, you could have the same kind of context where you have an atomic cooling halo, not necessarily bound as a satellite, but just nearby. As I said, it's a variation on the theme. And then you could still form the direct collapse black hole because you suppress star formation. But then what you could have is that you could have this DCBH instead. So you could have a little bit of star formation in that halo, and it won't necessarily merge with that one. But what you could have is an H2 region. So you could have a direct collapse black hole seed that is now in the center of a luminous H2 region. So they were able to kind of calculate some tracks in color space for what they would look like and whether they would be detectable by JWST. So it turns out that there are small periods of time where they may come within the detectability because otherwise it's quite faint, right? So I just want to point out this is another very, very interesting scenario, but the loop hasn't closed in terms of the relationship with the host galaxy. Remember the black hole seeds, right? One of the interesting things about black holes is that, of course, all of these black holes could have started with primordial black holes, right? We could have started with that. The only way, and we can never tell, looking at a black hole that's 10 to the 6 solar masses today, in and of itself, we can never tell how it formed unless we have some clue with regard to the host galaxy in which it's sitting. So the scaling relations are really telling you something a lot more about the origin of how these seed black holes form. So in this particular scenario, there have been predictions that have been made for, as I said, for in color space, not yet detected from JWST. They are actually dimmer than those overmassive black holes that I just showed you, that particular scenario. So here's another specific scenario. Then there's another really nice scenario here, and this is a lower redshift scenario, a scenario where you can probably start forming direct collapse, effecting direct collapse in merging galaxies, merging gas-rich galaxies that may or may not be themselves initially seeded with a black hole. They don't have to be. During the merger, you can form a very, very turbulent supermassive disk that could then form from direct collapse, give you a seed. So, but this is a process because you need well-formed gassy galaxies with stars as well. This is work done by Lucio Meyer and his group, and Pedro Capello is working. He's one of my former graduate students. And so they've been exploring this scenario to account for the very bright quasars at redshift 6. So remember, this is not relevant for the black holes. This scenario is not as relevant for black holes that you will be seeing at 10 or 11, because it requires well-formed massive galaxies to already have formed. However, this is another direct collapse channel to give you a heavy seed. Right? And so there have been many, many simulations now where seeding, as I said, you have to kind of adopt a seeding prescription because you cannot form them ab initio. And by now, there are several simulations where you have different algorithms for seeding that have been implemented. And I think Aklan told us today about another interesting experiment trying to beat the resolution limit of codes like Illustris and to do zoom-ins where you can actually look at smaller regions and resolve lighter seed black holes and more massive seeds despite the limitations of say, Illustris. So Astrid, for example, I'm very interested in these simulations, and me and my research group are working at the moment on analyzing these simulations. They have a very different seeding algorithm, and they seed on the basis of the initial mass function of direct collapse black hole seeds that we have all proposed in our early sort of analytic, semi-analytic papers. And the behavior is different, as we'll see later. So also here, I want to give a shout out to the many groups that are working on various aspects of direct collapse, the relationship of galaxy hosts and the gas content and the spectral signatures, the role of dust, etc. And I want to give a shout out to Tiziana Di Matteo's group, Marta's group, Michael Trammell's group, Rafaela's group, and Zoltan Hyman's group. I noticed it's almost all, not quite all Italians, right? Okay. Just like the Italian mafia has taken over black hole seeding here. Okay, so, no, later. I'll visit you later. Okay, so as I mentioned, there's also been some very interesting work. This is work that I'm particularly fond of because it was done with Tal Alexander, who is not with us anymore. Anyway, this is a very cute idea of trying to, as you can imagine, right? One can argue that isn't like light and massive kind of semantics. Could you just be born light and then very rapidly become massive? Sure. And as I mentioned, nuclear star clusters could be very efficient incubators for doing that amplification. So this is one sort of cute scenario that we came up with, where basically you have a nuclear star cluster, you have one of them, you have the first black hole that forms, that then scatters off the rest of the stars, and in sort of wind-fed accretion through a very gas-rich nuclear star cluster, it starts slowing down as it gets more and more massive, and it sinks to the center, and depending on how much gas there is to actually accrete in this sort of closed box system, you could end up with a whole range of masses. So depending on when the accretion actually stops, you could end up with a seed that is 5 to 10 solar masses, a few hundred solar masses, and up to 1,000 solar masses. And one of the things sort of developing this picture later on, I realized that an advantage of looking at slightly idealized way, oh my God, I have 5 minutes, okay. Looking at, okay, I'm going to go over time. So is that basically you could end up making black hole seeds at all times. So the question is, what are the signatures of seeding? So I told you that for the model, so these are the cooler colors are heavy seeds, the warmer colors are light seeds. So this is work done by Angelo Riccardi. And this is a semi-analytic model in which we looked at seeding and the impact down to low redshifts. Low here now for all of us, is 6 is already low, right? So what we find is these are luminosity functions, volumetric luminosity functions, whatever, done with a correction for the X-ray, so predictions were made for axis. We showed that heavy seeding should show up at very early times. So I want to stress the point that a lot of the signatures that we're talking about will show up at early times, closer and closer to the seeding epoch. So at high redshifts, you should start seeing, should be able to pick out seeding looking at the luminosity function. One of the key ways in which you could also disentangle seeding from dynamics and accretion physics, which are the confounding things at later times, is gravitational wave signature. So these are predictions for LISA, and of course lots of uncertainties here. I think it was alluded to earlier in that, you know, depending on whether, what you assume about the dynamics of merging black holes. If you're optimistic, you think every galaxy merger will lead to a black hole merger, then you still see with the cool curves being heavy seeds and the warm colors being light seeds, that there's very clear discrimination. This is the total number of events after 4 years. And this is a function of chirp mass and as a function of redshift. So you really should be able to tell. And interestingly, intriguingly, there is one signature that survives to late times, and that is the local occupation fraction. So this is the heavy seeds with a particular accretion model. So again, this is a library of accretion models. And this is the data, is what you see in black and triangles, and there is support. So let's just go back quickly to the DCBH particular channel that I talked about. And here, we will look at how formation of DCBHs in the scenario where I talked about a parent and a satellite, and the formation of this overmassive black hole where the mass of the stars and the mass of the black hole could even be comparable. So one of the interesting things is I want to show you close to the seeding epoch, if you permit heavy seeding in the universe, you will always be offset from the M sigma relation. And this is something that Marta and I realized way back when we were looking at the journey to the MBH relation in 2009, that you would start out, let me see if I can start this movie. Yeah. So this is again from a semi-analytic model, and this just shows you the clock, and this is just one instantiation. And what you see in the data points there at redshift 0, that's the M sigma relation. So what you see is that in M sigma, you are overmassive. And of course, in MBH M star, you will be as well, but only very close to the seeding epoch, right? That effect could get washed out. So these are the specific predictions that we made for the overmassive black hole galaxies. The cool colors, once again, these are the two different metallicities for the stellar component. So remember, we have this composite of the accreting black hole and the stellar component that's inherited from the parent. That is also aged, and these are predictions. Intriguingly, we plotted them for redshift 9 as a template in our paper. And so this is for the heavy seeds, and this is for population 3 seeds at the same epoch, so at redshift 9. And so you see that in our library of models, very few of them should be detectable by JWST. These are the Miri-NIRCam limit, sensitivity limits. So you see that the heavy seed models should be booming, and there is a very characteristic spectral shape. And so let me quickly show you how nature was very kind to us in the end. So there was a program where they started looking, as you all know, looking through the frontier fields. And for me, this was a particular pleasure, having modeled the dark matter mass distribution from gravitational lensing for all these fields and calibrating these magnification lenses, as it were. So Abel 2744 yielded two very interesting objects. So the case I really want to make and show you is that we have a trio now of redshift greater than 10 sources, UHZ1, which is at 10.1, and GHZ9 and GNZ11, which you've heard about from Hannah's talk as well. And I want to argue here that this trio is already showing us that we should have multiple seeding channels permitted in the universe. So here you see GNZ11, and what you see here are the fact that if you start from this is the initial seed mass, if you start from low mass seeds versus high mass seeds, if you start with a direct collapse massive seed, you just, with Eddington accretion, you can explain the properties. Whereas if you started with a light seed, you could do that, and you then would require super Eddington, episodes of super Eddington accretion, if not steady super Eddington accretion. Intriguingly, UHZ1 is this object which was the only accreting black hole so far detected in the X-ray. So I just want to point out here, remind you that this is now at 5 sigma. When we published the paper last year, it was at 4.6 sigma, and we now have the full data set. And so this is a deep Chandra imaging through Abell 2744. And GNZ11, we think, has not yet been detected in the X-ray. And remember, lensing is helping us, so it's magnifying these, and remember, lensing is achromatic, so this is lensed by a factor of 3.8. Another intriguing object, GHZ9, which is at a much higher redshift, and I think it is to be spectroscopically confirmed. I gather the data is in hand, but we don't know. It's detected at about 3.5 to 4 sigma in the X-ray, and this is magnified by a factor of 1.6 or so. So the interesting thing about UHZ1 is that it satisfies all the predicted properties that we published in 2017. And that is the multi-wavelength spectrum. So this is the measured Chandra flux. This is the JWST. And these are, once again, the tracks. And what we show here are that if you had, it could also have had super Eddington accretion, et cetera, except remember, for this direct collapse, we have provided multiple criteria that need to be satisfied, that we predicted the relationship with the host galaxy. And this one actually satisfies all of them. Okay, so the X-ray flux, it should be X-ray dominated compared to rather than IR dominated. So this is a comparison with the Candle's Goods Field South sources. And this is the spectrum of UHZ1, and this is one from our modeling library. So our best fit is Eddington limited accretion, and we see that with a heavy seed. So the black hole mass that's measured at redshift 10.1 for this one is a few times 10 to the 7. Okay, so I'll just wrap up here to tell you that, you either need modest growth of heavy initial seeds. This is the major discrepancy, sort of the degeneracy, versus accelerated growth of light seed. But what can resolve this kind of confounding thing is the properties of the host. That's why I'm so excited about the discovery of hosts and host properties. I just want to point out that we do need heavy seeding massive seeds, because in simulations to date, it seems quite hard to actually have the light seeds form in a cosmologically consistent way and to grow. And I think I'll skip this part, but I'll just show you this, which is, often we cannot do much with individual sources, but this is a special case where with these 3 redshift greater than 10 sources, we can actually say something quite conclusive about black hole seeding. But as you all know, that the key confounding things for black hole growth and evolution are the convolution of formation, fueling, and feedback, and how these couple, and that we typically use the black hole mass function and the quasar luminosity function. But what we would ideally like to get at, right, is that the accretion rate and the environment of the characteristic black hole at every epoch, right, so that we are not actually comparing outliers. I just want to advertise this database called Quotas, where we are looking at, we have compiled data and simulations of black holes at high redshift, and I will just point out. So one final point to make is that in many of these growth models, we are using these subgrid prescriptions. And there's very nice, I want to advertise this work by graduate student Heiran Cho at Harvard, working with Ramesh Narayan and me and our group, that has just shown that, it's a GR MHD simulation that now connects to much larger scales, from parsec, sub-parsec scales to kiloparsec scales. And we find that all simulations, cosmological simulations, assume that any gas that makes it past the Bondi radius gets accreted to the black hole. It turns out there's a 2 orders of magnitude suppression if you go from the Bondi to horizon scale. So that's something that we are hoping that we can provide new guidance to simulations. Okay, so what would we need? I think a single quasar. So speaking of single quasars versus populations, a single quasar that is a mass of 10 to the 6 solar masses at redshift 18 or 16 would further nail down seeding, because this is the place where the 2 seeding channels do not really overlap. So if you find one of them with the host, and we can show what the properties are. And so I'll just close with showing you that there's some very interesting work that can be done, that signatures of seeding might survive, but not out to redshift 6, because as I showed you, the evolution involves feedback. So what is another kind of clever way to maybe get at these seeds? Might be the disruption perhaps of a POP3 star tidally disrupted by heavy seeds at very early epoch, especially at redshift 10. So I'll just stop here. Thank you so much.
Questions for Priya? Start with Marta, and please say your full name.
Marta Volontieri. So this relates to something that you said at the very beginning about the connection between PTA and JWST, the overabundance, which is something that I've been also thinking in the last year. So historically, our theoretical models always predicted lots of faint AGN at high redshift. Exactly. And so we tried as much as possible to decrease them. So is this, I mean, could this be also the reason why we underestimate PTA, because we suppress so much to meet the non-existent AGN population that now exists?
Exactly, right.
That we also go in the same direction for PTA.
Exactly.
And I see this as a sort of continuum or a vicious circle. So do you agree with?
Absolutely, I agree with you, because I think that, you know, a lot of our earlier models were dictated, as I noted in a comment earlier, that there is a highly obscured, unseen population of AGN yet to be discovered, factors of 2 to 3, that between at least redshift, under redshift 5, as predicted by the modeling of the cosmic X-ray background. And so that's an unseen population, and so we all suppressed our models in order to match the multi-wavelength data of seen black holes. And now it turns out that, yes, it could be part of the issue, but I think that we also bona fide know that there is an obscured population, a Compton-Thick population. We may have to do some extrapolations, but I'm convinced that if we include that, we can explain the PTA signal. The amplitude is not an issue.
So, Simenton, and so can I ask, so you showed so accretion of the black hole in the later part, and so you said actual accretion rate onto the black hole might be
suppressed.
Suppressed. So is it true for general case or only in the superdentum case, or?
No, so this is in a very general GR-MHD case where we were trying to model M87, though. That was for the M87, not Milky Way. So this is starting with initial conditions that are consistent with the Event Horizon Telescope collaboration, estimates of the mass, the electron density, etc. from the EHT data. We used that as a starting point, and we looked to see how accretion around such a massive black hole, whether we could replicate the accretion rate. Starting with the right mass and the right conditions with a GR-MHD code, we used the code karma to see if we could replicate it. And we found that we could set up, and what we do find is that in the case of M87, this is no spin, assuming no spin, that actually the actual accretion rate on horizon scales is highly suppressed. So for example, in all cosmological simulations, because you are using the Bondi radius, you don't even resolve that most of the time, but whatever, even in cases where you sort of resolve that, you assume that any gas that passes through the Bondi radius ultimately grows the black hole. We increase the mass of the black hole by that. So it turns out now that that is not the case. However, notice that in all these cosmological simulations, the mass of the black hole also controls the amount of feedback. So obviously, if the mass goes down, the feedback will not be as strong either, which are all things that likely go in the right direction for some of the other problems that AGN feedback poses in galaxy formation simulations.
So while you're headed over there, I'm going to jump in with a chair's prerogative question. So this is Peter Bruzzi. If you go back to the slide about direct collapse formation, showing the cartoon where you have Lyman-Werder radiation, you say direct collapse black hole formation. Avishai Dekkel says feedback-free starburst. And to me, it seems like the main difference is whether the cloud becomes self-shielding or not. Can you talk more about if you get alternate scenarios besides direct collapse black holes?
Oh, you mean in this case,
systems,
whether you wouldn't form a black hole? No, we have not really investigated the full physics of, because we were really interested in trying to see if we could embed DCBH formation in the cosmological scales and the hierarchical growth that we see at early times. So we've not really looked at it. However, as I pointed out, nuclear star clusters, and I think I see what Avishai and others are doing, no different from the kinds of arguments that we're making about the nuclear star clusters behaving as incubators for formation of seeds. Both light, as I said, light and heavy seeds can be formed in nuclear star clusters. I think, Marta, you've done a lot of work on that too, right, with Pfister, that these can serve as pretty good incubators. And they may explain some off-center accreting black holes at earlier times. I think there's been one where there's a claim that maybe there's an off-center black hole.
Hi, this is Alex G. I was very struck by the fact that we haven't actually made a direct collapse black hole ab initio. And I'm reminded of the population 3 star simulations where, like, as you kept going higher and higher resolution, the mass of the resultant objects went
you
down.
had more than one star.
Yeah,
the entire time I was in graduate school, there was the first star.
Right.
And then it became stars.
Yeah. And so I'm wondering, but you sound not worried about that in terms of this seeding scenario. And should I feel worried? Is this not really a problem, if that makes sense? Especially because we just saw that,
Yeah, so I think I think it's a different problem because these turbulent cores that do form are so dense that they will inevitably, by post-Newtonian GR instability, really become a black hole. You're right that the question is, what is the mass of that thing compared to the mass that's in the turbulent core? We don't quite know, but what we do know is that turbulent cores are actually much more massive than we think even a POP3 star would be. So you will definitely end up with a much more massive seed than you would, unless of course the POP3 IMF is tilted heavy in a weird way, and I don't know, that's an open question. So I mean, that's the thing, right? For all the belief in POP3 black holes, light seeds, we don't really know what the IMF looks like, right? So we're still very much, it's sort of an open season, I would say, for theorists, right?
Thanks.
Other folks with questions? All right, maybe Alessandra can come up. Thanks, Priya.